Okay, hello students. My name is Songjie Huang. Today I'm going to introduce you one of research verifying JVMs using differential testings. We particularly focused on J9 implementations on JVMs in this research. So in these sessions, I will introduce you the methodologies that I use to verify J9 implementations and some of bugs that I found during this research. So let's begin. Before going into detail, let me briefly introduce you the J9. J9 stands for Java Native Interface, and it provides a way for Java application to interpret with native code written in C and C++. So using a J9, Java applications can call functions in native code. And similarly, the native code can invoke method in Java, or it can access classes and fields defined in Java applications. So J9 is very useful in developing an efficient program because C, the native code is generally much faster than Java applications. So Java developer can implement the performance critical logics in the native code, and using a J9, Java can use this native code written in C. So if you analyze many game applications in mobile phones, most part or core logics of the games are written in native code, not using Android, Java, or Kotlin. The another benefit of using J9 interface is that the Java applications can reuse standard library implemented in the native code. So J9 indeed gives some benefit to Java developers. So most JVMs support the J9, and the JVM vendors provide the J9 features by complying the J9 specification developed by Oracle. So this is the J9 specifications developed by Oracle. All JVMs that support J9 follows these J9 specifications. Even though J9 gives some benefit to developers, it is not easy to develop correct J9 program because of interpretations of two different programming language. As you can see here, if we develop program using a J9, we have to use Java and the native code. And these two different programming languages are interpreted through the J9. And this is not simple, it's complex task because these two languages has a different syntax. Java and C has a different syntax, and they have different types, and they have different semantics. For example, C, we can control the low-level memory by using a pointer, but we cannot access low-level memory in Java because there is no pointers. The Java automatically manages the memory by using a garbage collector. So these differences leads to the complexity of programming, and that leads to the bugs in the programs. Moreover, there is no good tools for debugging and validating JNI programs, so it's very difficult for developers to debug when they develop the JNI program, so there might be hidden bugs in your JNI programs. So since there is no good debug tools for JNI programs, it would be great if JVM validates invalid usage of JNI function automatically for you in runtime. So we evaluate the JVM so that they validate the invalid use of JNI functions in JNI programs. This is a very simple source code showing the very simple example showing how Java and native code interpret each other. So this is a Java side, and this is a native code written in C. In Java code, native code are declared with native keyword here. So here we define native code, function name foo, return type is string, which is correspond to this one, the foo functions. And once you declare the native functions using a native keyword, Java program can use this native keyword just like a Java method. As you can see here, Java program call the foo method here, and you receive the return type. It uses the foo, the native function, just like a Java method. On the other hand, native code can also call Java method. In this example, it tries to call the Java method name. But this native code is looks more complex than the Java code. In Java code, we just call this native code by in a single line, but in native code, if you want to call this Java method, you need to make a sequence of API JNI calls. So here you first call the getObjectClass method. This is also JNI functions. You receive the Java class by calling this getObjectClass, and then by using this Java class pass as a second argument to this getMethod ID. So by calling the getMethod ID with the Java class that you received here, and by giving a function name and the return type of the functions, you can obtain the Java method ID here. So after this line, you receive the method ID of these functions. And by using this method ID, by calling this, and by calling the getObject, by calling the callObject method using this method ID here, you can call the Java method name here. So the red functions are all JNI functions. So to call this Java method, we made a sequence of JNI API calls here. So this is how native code in JNI program looks like. So let me give you an examples of unspecified cases in JNI specifications, because we utilize these unspecified cases to find the JNI bugs. So this screenshot shows the JNI specifications explaining throw new JNI functions. It says that the second argument of the throw new. So first of all, JNI specifications, you can find the JNI specification in this URL. The 90% of JNI specifications is about describing the JNI function shown here. So as you can see here, the function signature is here, and you can see the types of the parameters and the number of the parameters for the JNI functions. And there is a descriptions about these JNI functions. And here you can see the conditions that the parameter argument should satisfy. And it also explains the return value of the JNI functions and possible exceptions when something goes wrong while executing these JNI functions. So 90% of JNI specification is about explaining JNI function as shown here. And this screenshot is describe the through new JNI functions. It says that if you look at here, the second arguments of throw new JNI function should be a subclass of java.lang.throwable class, and the value must not be null. So this is explicitly specified in JNI JNI specifications for the throw new JNI functions. However, it does not explicitly explain the JVM behaviors when non-throwable object is passed to the second arguments of throw new JNI functions. And because JNI specification does not explicitly describes the behaviors, the semantics of when non-throwable object is passed for the second arguments, that cases may lead to some issues in some JVMs. We call such cases as unspecified cases because JNI specification does not explain about it. And we believe that these unspecified cases are a very useful resource to validate the JVMs, particularly for the JNI implementations on JVM vendors. This is another example of the unspecified cases. In this example, the JNI specification explains about register native functions. If you look at here, the false arguments must be greater than 0. This is the explicitly stated in the JNI specifications, but it does not explain about what JVM, how JVM should behave when the false arguments are the 0 number or the negative number. So this is another example of the unspecified case in the JNI specifications. During this research, we found a lot of unspecified cases in this research, and we tested. We developed the test program that triggers the behavior of the unspecified cases, and we actually execute these test programs and see how whether JVM vendor correctly validates such unspecified cases. We believe that JVM should validate such cases because that is incorrect use of incorrect use of the JNI function. So we believe that JVM should validate all or most of the unspecified cases that we have found in this exam, in this research. But we encountered that JVMs do not validate almost all of the unspecified cases that we have found during this research, which seems very bad. We have communicated with JVM vendors for these issues, not validating unspecified cases during runtime. And the JVM vendor said that they intentionally do not validate unspecified cases due to the performance issues. Because if they validate unspecified cases in runtime, that definitely degrade the JVM performance. Moreover, they also point out that the JNI specifications also says that it is the developer's responsibility not to misuse the JNI functions shown here. It is your responsibility to ensure that NUR is not passed to the JNI functions. So this is the reason why JVM does very little error checking in JNI interpolations. But we also found this option X check JNI in JVM. This is debug options. When this option is on, JVM do additional validation on the argument passed to the JNI functions. And our communication with JVM vendors reveal that they want to validate as many error cases as possible when this option is on. So if you look at this example, if this option is turned on and if we execute the test program that triggers the unspecified, the behaviors of unspecified cases, JVM validates such. We found that JVM validates some of the unspecified cases and shows the error message shown here. If this option is turned off, JVM do not validate the unspecified cases and does not show this error message. So in this work, we evaluate this XCheckJ9 debug capabilities in 5 mainstream JVMs using unspecified cases. We check whether the debug capability validate unspecified case properly in this research. For that, we developed the JustGen. In order to understand whether JVMs, particularly for the XCheck J9, this one, the debug capabilities implemented in JVMs, we check whether that debug capability validate the unspecified cases properly during the runtimes on these 5 mainstream JVMs. So to automatically validate XCheck J9, we developed JustGen. This is how JustGen looks like. The input for JustGen is a J9 specification expressed in our domain-specific language. JustGen first automatically convert this input data to bit vector, express it bit vector here because we are using SMT solver. SMT solver can understand the bit vector, so we transform this DSL, the JNI specifications in DSL into the bit vectors. And using SMT solver, we find the unspecified cases in the JNI specifications automatically. So by running these tools, we found that 34,990 unspecified cases. And in this test code generator module, it received the unspecified cases and generate the test program that triggers the behaviors of the unspecified cases automatically. And by running these test programs on the 5 mainstream JVMs, including the hotspot from Oracle and OpenJ9 from IBM, we validate the extract J9 options in these JVMs. And because different JVM produce different outputs, in the assembler module, it assembles all the outputs from different JVMs and normalize the output data and compare the output results. So if there is some difference results between these different JVMs, that may be the bug. So we perform the differential testing for verifying the JVMs. Differential testing is very good because we can find bugs even though we do not have a ground truth by comparing the results from the different JVMs. If we look our tool into more detail, the first part is transforming J9 spec that is written in natural language to mechanized spec, which is represents in our DSL here. DSL stands for domain-specific language. We develop it in a way that it can be used to represent the necessary information in J9 specifications. So for example, function name, the types of parameters and conditions for the argument values. We can use our DSL to represent such informations. We transform the J9 spec into the spec represents in our DSL because it is difficult to do something automatically with the original J9 spec as it is written in a natural language. As you probably already know that the natural language is very ambiguous, so it's always very difficult to do something automatically with the natural language data. So this DSL is very simple. T can be a primitive type or predefined types specifically for the J9. And the P is a refinement predicate indicating the condition that the type of input must satisfy. And R is a refinement. It can be P or a conjunction of R. And spec and unspec represent whether, so the K can be spec or unspec, and it's shown here. It represents whether these conditions are specified or unspecified. So if K is unspecified, these conditions are unspecified. If K is specified, these conditions are specified in the J9 specifications. So let's see the concrete example. So in this example, set int array region J9 functions are represented in our DSL. As you can see here, the spec keyword is used here. So this is the specified conditions. So if we look at the second argument, the second arguments, the type of the second argument is a JInt array, and this is the refinement. It indicates the conditions that the second argument must be satisfied. So it says that not null means that the second argument must not be null. And because this is in the spec, because this is with the spec keyword, the specification explicitly state that the second arguments of set int array reason GNA functions must not be null. So we transform this into the big vector, which can be understood by the SMT solver. And using these equations, the SMT solver can find the unspecified cases. For example, here, because specified is a not null, passing null value for the second argument is unspecified cases. Our tool, the SMT solver, knows that and generate and find this unspecified case automatically. So it's SMT solver using this equation, SMT solver find one unspecified cases and add that condition into our DSL, and it iterate again. It loops this it iterates these loops and find all the unspecified cases. And once the SMT solver find all the unspecified cases, it goes out this loop and move on to the next step. So in the next step, the unspecified cases are written in our DSL, for example, here. So this information is passed to this test code generator modules and the test code generator modules receive the template code as well and generate the test program that triggers the unspecified cases automatically. So for example, here, this is the example of the test code that is generated by the test module, test code generator module. So these parts are auto-generated. So as I explained in the previous slide, J9 programs are the sequence of J9 function calls. So as you can see here, this is a J9 function, this is a J9 functions, and this is J9 function. There is a sequence of J9 function calls. So these codes are automatically generated by this test code for unspec modules, and this code triggers the behaviors of the unspecified cases that we have found in the previous phase using SMT solver. And by running these test programs on different JVMs and comparing the results, we identify bugs in the JVMs. So by running our tool, we found a lot of abnormal behaviors from JVM due to the lack of validations, even debug options. The xcheck J9 is turned on. So we summarize the result into 4 different categories: the misbehave, seg fault, exceptions, and validations. The misbehave category represent that the test case terminates normally without any warnings or errors. So since behaviors of unspecified cases are not explicitly defined in the GNS specifications, each JVM may produce different execution result here. And that may lead to serious and critical problems. And the seg fault represent that the test case causes segmentation fault or crashes on JVMs, and the exception represent the JVM, so the exception while executing the test programs. And validations represent that JVM properly validate the test cases and terminate with an error message or warnings, which is a good thing. We further evaluate the cases for the misbehave category, and we found that 12 abnormal behaviors from JVMs because of the unspecified cases. Among them, I will introduce you 2 findings here for the time limitation. Please see our papers for other findings as well. So our first finding in misbehave category is error handling issues. So this is the cases where JNI function returns incorrect return values. So upper side shows the test cases. The test program that triggers the unspecified behaviors. So if you look at the bottom side, the JNI specification says that the first argument for the register native function must be greater than 0. But our tool found that passing a negative number for these register native functions is unspecified cases and generate these test programs. And by running this test program, we found the different results from different JVMs. The OpenJ9 returns -1, and other JVM returns 0. The interesting is that if we look at the specifications below here, the return values, the 0 indicates the success, and the negative value indicate the failure for these register native JNI functions. Since it is not possible to register the negative number of native functions, the -1, this register native function code should be failed. But as you can see here, only the OpenJ9 returns -1, which seems the correct return value. Other JVM returns 0, indicating that they successfully registered the negative number of native function, which is not understandable. So this is the cases we found issues in error handling from JVMs. The second finding is a deadlock. This is an interesting issue because this problem only occurs when the debug options is turned on. So this is the case where the bug exists in the debug capability in JVMs. If you turn off the debug capabilities, this problem does not occur. So in this example, release into array elements is a JNI functions. For the third argument, for this release into array elements, must be retrieved from this get primitive type array element JNI functions. So passing the elements not getting from these JNI functions is unspecified cases. So our tool generate this test program passing null values, which is unspecified cases for this release into array elements. By running this test program, we found that OpenJ9 hangs, as shown here. And other JVM successfully validate such unspecified cases and throw error message showing that element vector is null value. We report this issue to IBM, and they released patches very quickly. If I remember correctly, they released patches within 24 hours. So the IBM's, the OpenJ9 community is very active. We also studied in which cases triggers the segmentation fault on JVMs. There were a total of 4 cases shown here. Missing type check is where the usage of the incorrect type of values or objects. So for example, from reflect method, expect to receive java.lang reflect method or the constructor type of objects for the second arguments. But our tool found that the passing throwable types of object is for the second argument of from reflect method is unspecified cases. And if you run this code, it triggers the segmentation fault for all 5 JVMs. So JVM do not validate such incorrect types of object usage in this from reflect method. We also found that segmentation fault occurs because of missing null check and liveness check and releasable check. The missing null check is the cases where JVM failed to validate the uses of the null values. So according to the JNA specifications, we should not pass it the null value for the third argument of this core int method. The missing liveness check is the case where deleted reference objects or values are used by the JNA programs. And the missing releasable check is the cases where the JNA function release object that cannot be released. So here, release int array element should be used for releasing the int type of array elements, but we passes the string type of array elements, which is incorrect, and this is also unspecified cases according to the general specifications. So these kinds of unspecified cases leads to the segmentation fault on JVMs. We did not further explore the cases where JVM throw exceptions because we think that it is the correct behaviors from JVMs. Instead, we further studied the validation category. Here we compare the debug capabilities between different JVMs. As you can see from this table, OpenJ9 validate most unspecified cases compared to other JVMs. Moreover, Zulu and Creto validate exactly the same number of the unspecified cases, which indicate that they have the same debug capabilities. And Hotspot, GraalVMs are also have a also validate similar numbers of the unspecified cases. So this indicates that Hotspot, Zulu, Creto, GraalVM have a similar debug capabilities. Only the OpenJ9 has a significantly different debug capabilities, and among them, OpenJ9 is the best. But there were no perfect one, as you can see this table. There is a cases where hotspot validate where OpenJ9 could not validate. So, and this right side of the table shows that the unspecified cases where all five JVM could not validate. So it is recommended that if you try to validate your JNI program using a debug capability provided by JVM, it is recommended that you should validate your JNI program using hotspot, OpenJ9, and one of the other JVMs, for example, hotspot. So by doing that, because JVM vendor validate different kinds of unspecified cases that we found. So if you validate your JNet program using multiple JVMs, you can validate more of the unspecified cases compared to the validating JVMs, but compared to the validating your JNet program using a single JVM. We report the 792 cases, and 563 cases are currently fixed by OpenJ9. We also expect the patches from the other JVM in near futures. Okay, thanks for listening my talks. This research is the example of how we use the differential testings for validating the G9 implementations on JVMs, and we use the unspecified cases for testing the JVM in this research. Okay, thanks for listening my talk. Let's see you again in the near future in other class. Thank you.